So the first important memory consistency model, and also the simplest, is sequential consistency. And it was published by Leslie Lamport in 1979. Leslie Lamport is famous for many things, including the LaTeX macros for tech, and also a method for parallelizing loops that we will look at in a later lecture. In the sequential consistency, we can view the machine as if it has no cache memories. It is implemented with cache memories, but the mind model of it when we program is that it has no cache memory. So every thread or CPU performs one instruction at a time concurrently, but all the memory accesses are done atomically. Okay, so you can view this as a number of CPUs and then the memory in one place, and the memory lets one CPU access it at a time. Okay, and neither Java, pthreads, C++ or C require it. Okay, a practical view of sequential consistency is that the program order for each processor is maintained. And what does that mean? Well, the CPU is not allowed to switch the order of memory instructions. So they are performed in the order as written by the programmer / compiler, because the compiler will introduce some more memory access instructions. And all memory accesses can be thought of as being atomic. And what does that mean? Well, that no two memory accesses are happening at the same time. Okay. Now a note. It is that the C standardization committee first considered using sequential consistency as the default memory model for C. But it was convinced that the C++ standardization committee were more competent in deciding on a suitable memory consistency model, and they simply copied basically everything. And that was really a good thing to do, since they are equivalent, except of course for some syntax differences, but that's not very important. Okay, so let's look at the definition of sequential consistency, and this is Lamport's definition. I just read it. A multiprocessor system is sequentially consistent if the result of any execution is the same as if the operations of all the processes were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. Okay, so what does that mean in practice? It means that we can take all the memory accesses and put them in a sequence, because they are not overlapping. Okay, so this has far-reaching practical consequences for how we can write programs. So if we look at these three variables and three threads, and as we can see, all the variables are 0 from the beginning, and then thread 1 writes 1 to variable A. There is a time in this as well, and this is the first thing that happens. And then thread 2 checks if A is non-zero, and if it is, it writes B. I mean, it writes 1 to B. And then thread 3 checks if B is non-zero and writes the value of A into C. Okay, so since all memory accesses are atomic, if B sees the value 1, then A must have the value 1 as well. That sounds like a good thing, but for relaxed memory models, that is not the case. Okay, and what is it that we rely on for this to happen? Well, it is that they occur atomically, and then since this one is atomic, then all the other CPUs must see the same value. So there is no risk that T2 sees this value first and writes to B, and then B observes the value of B but has not yet seen the value of A. Okay.